Hi there, I'm Sridhar Chandrasekharan, and I'm presenting a study series on power transmission line construction. Drawing from my extensive career experience, this series is designed to provide practical and theoretical insights that can be directly applied to real-world projects. We began this journey by exploring the basics of electricity, how it's generated, its requirements, and its sources. From there, we've covered critical stages such as tendering, bidding, and project initiation. Moving forward, we'll delve into implementation, execution, and finally project handover. Given the complexity of this topic, the content is divided into chapters released weekly. Along the way, we'll also integrate discussions on essential complementary areas, including engineering ethics, legal considerations, health and safety compliance, human resource management. These vital aspects will be seamlessly woven into our technical discussions to provide a holistic perspective. Each week, I'll release a new video featuring key technical topics, ethical dilemmas and considerations, a thought-provoking quote to inspire meaningful reflection. Currently, we're in Chapter 12, trying to understand the construction activities started with survey. There's still so much more to discover, so stay tuned for the upcoming chapters. Thank you for joining me on this journey of learning and growth. Disclaimer. Just a quick note. The content in these videos is meant for informational and basic educational purposes only. These videos aren't intended to provide professional advice or endorsements. This helps set the right expectations about the nature of what we're sharing, especially since we draw on material from various sources under the principle of fair use. In Chapter 11, we began discussing with construction activities, covering topics such as site handover and some aspects of survey activities. In this chapter, we will continue exploring the remaining topics related to survey activities. Since the subject of surveys involves various subtopics, it is challenging to cover everything in a short time. Therefore, we are taking a step-by-step approach to briefly explain each topic. As mentioned in earlier chapters, the focus is to provide knowledge about how the subject functions, rather than delving into the detailed methodology of execution. Now, let's move forward to uncover the remaining topics on survey activities. Stay tuned. As we delve deeper into the full range of construction activities and their corresponding procedures, we will follow a logical and systematic sequence from start to finish. Each task will transition seamlessly into the next, ensuring smooth and efficient progress throughout the construction phase. The key topics to be covered during the construction phase, as previously outlined, include a variety of subtopics. Let us now outline the main areas of focus for transmission line construction. 1. Site handover, covered in Chapter 11. 2. Survey, was introduced in Chapter 11, where we covered some topics, and we continued to expand on them in this chapter. In Chapter 13, we will complete all discussions related to survey activities. The following topics will be explored in greater detail in the upcoming chapters. 1. Coordinate system, ode, ellipsoid. 2. Bush clearing, tree cutting and access road. 3. Soil investigation. 4. Foundation. 5. Tower erection. 6. Stringing. 7. Checking and energizing. Stay tuned as we explore these topics in greater depth. Survey process in transmission line projects. The construction phase begins when the contractor starts establishing a base at the project site. While this phase requires various clearances and approvals, as discussed in our earlier chapters on project management, the contractor often initiates fieldwork early by starting preliminary survey activities. Contractors typically aim to avoid delays by beginning initial survey activities even before formal site clearance is obtained. However, obtaining site clearance from the client and the chief engineer (CE) remains mandatory, as emphasized in previous discussions. In Chapter 11, we covered the following survey topics. A. Route survey. B. Detailed survey. The remaining topics will be covered in this chapter and subsequent ones, including C. Profiling submission and approval. D. Check survey. E. cross-diagonal profile. F. Geographic coordinate system. Stay tuned as we dive deeper into these critical topics in the upcoming sections. Let us now move on to the next stage of surveying, following the completion of the detailed survey and the handover of the necessary data to the design team. This step enables the design team to initiate the profiling and tower spotting processes. Let us explore this topic in greater detail. Profiling and submission. Once the design team receives the site survey details, they also require other technical specifications and approvals to prepare the profile accurately. These include conductor specifications, tower types, span lengths, environmental conditions, design criteria for transmission line and to ensure efficiency and reliable operation throughout its lifespan. These criteria are guided by engineering principles, operational requirements, and compliance with local and international standards. Profiling. Details required for plotting are defined. 1. Design criteria. 2. Site details to have already been made. So let us explore about the requirements of design criteria. Let us venture the first topic, design criteria on profile submission. Design criteria. Many of the design parameters are provided by the client during the tender stage, including technical specifications. Some of them are documented from the local authorities, for example, wind zone and peak flood level. The generated criteria are then submitted to the client or consultant engineer, CE, for their review and approval. Once approved, we can proceed further with the project. This initial document submission is a crucial step, which we have very well covered in Chapter 10 on document submission and approval. Design parameters required are as mentioned. 1. Voltage level. 2. Load capacity. 3. Conductor design. 4. Line configuration. 5. Environmental and terrain condition. 6. Tower structural requirement, electrical design. 8. Reliability and safety. 9. Regulatory standards. Let us understand each topic of design criteria in brief. Starting with voltage level. Though we have covered this topic in our initial chapters, to brush up, let us understand in brief. Voltage level is a critical subtopic in the design criteria of transmission lines as it influences the entire system's efficiency, safety, and reliability. Let's break it down. Transmission voltage. The operating voltage level of a transmission line is one of its key parameters, usually specified as 33 kV, 132 kV, 400 kV, or higher, depending on the project, determined based on factors like power demand, distance to be covered, and the grid requirements. For short distances and lower demand, lower voltage levels like 33 kV might suffice, while longer distances with higher loads require higher levels, such as 400 kV or 765 kV, to minimize transmission losses. Higher voltage reduces current for a given power, minimizing resistive losses and allowing more efficient energy transport over long distances. Insulation requirements. Insulation ensures that the transmission line operates safely without electricity escaping into the surroundings or causing faults. Voltage surges. Insulation must be designed to handle fluctuations caused by switching operations, lightning strikes, or load variations. Environmental conditions. Humidity, temperature, pollution, and altitude can affect insulation performance. For instance, in humid or polluted areas, materials with higher dielectric strength and longer creepage distances are used. In high-altitude regions, reduced air pressure may require additional insulation. Insulation and clearances between conductors and between the conductor and the ground or structures must comply with safety standards to prevent flashovers. By carefully selecting the voltage level and ensuring adequate insulation, designers create transmission systems that meet both technical and regulatory standards, ensuring efficiency, safety, and longevity of the infrastructure. Load capacity. It is another crucial factor in the design criteria of transmission lines, as it defines the line's ability to handle electrical power safely and efficiently without overheating or experiencing excessive sag. 1. Power demand. The load capacity is determined by the amount of power the transmission line is required to carry, measured in megawatts, MW. This depends on the load centers, cities, industries, or regions, and their projected energy requirements. A transmission line with inadequate capacity can lead to overloading, increased line losses, and a higher risk of power outages. Number 2. Conductor selection. Commonly used conductors include aluminum, steel-reinforced aluminum, ACSR, or advanced composite materials. The conductor must be selected based on its ampacity, maximum current it can carry without exceeding its thermal limits. Overloading a conductor can cause excessive heating, which weakens it and increases line sag. 3. Weather conditions. High ambient temperatures can reduce the line's ability to dissipate heat, lowering its effective load capacity. Wind cools the line, increasing capacity, whereas ice buildup adds weight and increases sag, reducing capacity. Optimizing the load capacity ensures minimal energy loss during transmission. Avoiding overloading prevents overheating, conductor damage, or accidental contact with the ground or other structures. Adequate load capacity ensures uninterrupted power supply, even during peak demand. By carefully assessing the load capacity during the design phase, engineers ensure the transmission line operates efficiently, safely, and reliably over its expected lifespan. Conductor design. It involves selecting and configuring the appropriate conductor material and structure to efficiently and safely carry the electrical load while withstanding environmental and mechanical stresses. 1. Material selection. Aluminum is widely used due to its lightweight and good conductivity. Copper is higher conductivity but heavier and more expensive than aluminum. Composite conductors are modern materials like aluminum conductor composite core, ACCC, or aluminum composite reinforced, ACCR, are used for high-capacity lines. Steel-reinforced conductors are aluminum conductor. Steel-reinforced, ACSR, combines aluminum for conductivity with steel for mechanical strength. 2. Current carrying capacity determines how much current the conductor can carry without overheating. Ampacity depends on conductor material, diameter, ambient temperature, and cooling conditions, wind and weather. 3. Mechanical strength. The conductor must withstand mechanical loads such as wind pressure, ice accumulation, and its own weight. Tensile strength ensures the conductor doesn't break or deform excessively under load. 4. Voltage level. The conductor's insulation level and spacing are determined by the operating voltage. High voltage lines require larger conductors to minimize corona loss and maintain voltage stability. 5. Sag and tension. Conductor sag must be minimized to maintain ground clearance and prevent safety hazards. Tension calculations ensure the conductor can withstand mechanical forces without excessive sag or snapping. 6. Corrosion resistance. Conductors are often exposed to harsh environmental conditions, including moisture, salt in coastal areas, and pollution. Protective coatings or materials with corrosion resistance, like galvanized steel or aluminum alloy, are often used. 7. Thermal expansion. Conductors expand and contract with temperature changes, which affect sag and tension. Proper design accounts for these variations to ensure safe operation under all weather conditions. Conductor design matters to improve the efficiency by minimizing transmission losses by using materials with high conductivity and optimizing cross-sectional area. Ensures the line meets clearance requirements and withstands mechanical and electrical stresses. Balances material costs with performance to ensure a reliable and economical design. Prevents failures due to mechanical overloads, corrosion, or overheating. By carefully designing the conductor, engineers can ensure that the transmission line operates reliably, efficiently, and safely over its entire service life. Line configuration refers to the physical and electrical arrangement of conductors in a transmission line. It plays a crucial role in determining the line's performance, efficiency, and compliance with safety standards. For the design criteria, line configuration ensures the transmission line can meet load demands, maintain voltage stability, and operate safely in all conditions. 1. Single circuit versus double circuit lines. Single circuit consists of 3 conductors for 3 phases or 6 for bundled configurations. used for moderate power demands or lower voltage levels. Simpler to construct and maintain. Double circuit consists of 2 sets of 3 conductors or 6 bundled conductors per circuit, used for high power demands or to optimize transmission capacity in limited corridors. Offers redundancy and operational flexibility. 2. Conductor spacing. Proper spacing between conductors reduces corona loss, energy lost due to ionization of air, and radio interference. Adequate spacing minimizes electromagnetic interference, EMI, with nearby systems and ensures safe operation. 3. Phasing arrangement. The arrangement of conductors ensures balanced current distribution across all phases. Optimized phasing minimizes magnetic fields and reduces transmission line losses. 4. Bundled conductors. Bundling refers to using multiple conductors per phase to reduce electrical losses and improve efficiency. It also minimizes the effect of corona discharge, particularly for high voltage lines, for example, 220 kilovolts and above. 5. Horizontal versus vertical configuration. In horizontal configuration, conductors are arranged horizontally on the tower. Simplifies tower design but requires more space. Whereas in vertical configuration, conductors are arranged vertically. Saves space but may require taller towers, often used in urban or restricted areas. 6. Ground wire, earth wire. Placement. Ground wires are typically placed above the conductors to protect the line from lightning strikes. They act as shields, conducting lightning surges to the ground and protecting the system from overvoltage damage. 7. Clearances. Phase-to-phase clearance. Ensures no electrical faults occur due to close proximity between conductors. Phase-to-ground clearance maintains safe distance between conductors and the ground to prevent arcing and ensure public safety. 8. Tower design. Impact. Line configuration affects the design of transmission towers, including their height, weight, and load-carrying capacity. Towers must accommodate the spacing, arrangement, and weight of conductors while maintaining structural stability. Line configuration matters to optimized configuration, reduces power losses, and improves reliability. Ensures compliance with clearance and insulation requirements to prevent accidents. A proper configuration minimizes land usage and reduces construction costs while maintaining performance. Provides flexibility for future capacity upgrades or operational changes. The design criteria for line configuration determine how conductors are arranged to achieve the desired electrical, mechanical, and safety performance. By selecting an appropriate line configuration, engineers ensure the transmission line meets the required operational and regulatory standards. Environmental and terrain considerations. When designing a transmission line, the environmental and terrain conditions play a vital role in determining the line's safety, reliability, and long-term sustainability. Below is an explanation of how these considerations apply to specific aspects like ground clearance, wind and ice loading, terrain profile, and environmental impact. 1. Ground clearance. The transmission line must meet specified clearance levels above the ground to ensure safety and accessibility. Prevents accidental contact with conductors, ensuring safety for people, vehicles, and animals. Maintains functionality during high-temperature operations when conductors sag. Over roads, the clearance allows for safe passage of vehicles, including heavy trucks. Over rivers, the clearance ensures boats and ships can safely pass without risk of contact. Over railways, it maintains enough height to avoid interference with trains and overhead equipment. Over open land, it accounts for agriculture, grazing, or future land use while keeping conductors safe. 2. Wind and ice loading. Transmission lines must be designed to withstand forces from wind and the additional weight of ice. Prevents structural failure or conductor damage during extreme weather. Ensures line stability and operational reliability under variable conditions. Wind loading takes into account local wind speeds, especially in areas prone to storms, hurricanes, or cyclones. Ice loading. In cold climates, designs must handle the added weight of ice accumulating on conductors and structures. Combined effects. The structure should account for simultaneous wind and ice loads, which exert different types of stresses. Number 3. Terrain profile. The line must be adapted to fit the terrain, accounting for elevation changes, natural features, and human-made crossings. Ensures the stability of towers and conductors on uneven or difficult ground. reduces construction and operational challenges by preemptively addressing terrain-based obstacles. Elevation changes requires careful tower placement and variable heights to maintain conductor tension. Crossings adapts to rivers, highways, railways, and other features to maintain ground clearance and safety. Uneven ground. In hilly or rocky areas, specialized foundation designs are necessary for stable tower placement. 4. Environmental impact. Minimize disruption to ecosystems and comply with environmental regulations. Preserves natural habitats and biodiversity. Ensures compliance with environmental laws, reducing delays and penalties. Enhances project sustainability and public approval. Avoids unnecessary clearing of forests, protects wetlands, and minimizes soil erosion. Prevents harm to wildlife, e.g. using bird diverters, and ensures noise and electromagnetic fields are within permissible limits. Mitigates risks to water bodies, vegetation, and agricultural lands near the line. Addressing these environmental and terrain considerations ensures that the transmission line is safe, functional, and compliant with regulatory standards. By accounting for ground clearance, wind and ice loading, terrain profiles, and environmental impact, the design can adapt to local conditions and promote a sustainable, efficient, and reliable power transmission system. Structural requirements. Structural requirements are critical for ensuring the stability, safety, and reliability of transmission lines. They address the mechanical and electrical aspects that support the line's performance over its life cycle. Below is a detailed explanation of the key components. 1. Tower design. Towers are the primary structural components that support transmission line conductors. Their design must account for height, weight, and material to withstand environmental and mechanical loads. The tower height determines the clearance between the conductors and the ground or obstacles like roads, buildings, or waterways. Taller towers are used in areas with valleys, rivers, or other geographical features that require larger spans. Towers' weight must support the combined weight of conductors, insulators, and fittings under normal and extreme conditions like wind and ice loading. Includes additional allowances for dynamic forces like conductor tension and vibration. The tower material are commonly constructed using galvanized steel to provide durability, strength, and corrosion resistance. Alternative materials like aluminum or composite materials may be used for specific conditions. Design standards must comply with national and international standards like IEC or for structural integrity and performance. 2. Foundation. The purpose of foundations: anchor the towers to the ground and distribute mechanical loads into the soil, ensuring stability under varying conditions. The key considerations are: 1 is the type of soil, as foundations are designed based on the soil type, rocky, sandy, clay, etc., as soil strength directly affects tower stability. Soil investigation reports guide the design process. 2nd is load conditions, must withstand axial loads, vertical forces, and lateral forces, wind and conductor tension. Includes allowances for uplift forces in areas prone to windstorms or unstable soil. The common type of foundation is pad and chimney, used for stable soils. Pile foundations, suitable for weak or swampy terrains. Rock anchors, employed in rocky areas for secure anchoring. 3. Grounding and shielding. The purpose is to ensure electrical safety and protection from lightning strikes or faults by integrating grounding and shielding measures into the design. The components are: 1. Overhead ground wires or shield wires, installed above the phase conductors to intercept lightning strikes and direct the energy safely to the ground. Reduce the risk of equipment damage and power outages. 2nd, grounding systems. Properly ground the towers to ensure fault currents are safely dissipated into the earth. Includes ground rods, mats, or chemical earth electrodes, depending on soil resistivity. 3rd, lightning protection. Essential for safeguarding the transmission line and connected equipment from surges. Shield wires, surge arresters, and grounding systems work together to minimize damage. By integrating tower design, foundation design, and grounding shielding systems, the structural requirements provide a solid framework for the safe and efficient operation of transmission lines. These considerations ensure that the system can perform reliably under all mechanical and environmental stresses. Electrical design. Electrical design is a critical aspect of transmission line planning that ensures efficient power transfer, minimizes losses, and guarantees the system's safety and reliability under normal and fault conditions. Below is a detailed explanation of key electrical design considerations. 1. Impedance and losses. The purpose is to reduce power loss during transmission and improve overall system efficiency. The key factors are: first is resistance, minimized by selecting conductors with high conductivity, e.g., aluminum or copper. Lower resistance reduces heat generation and energy loss over long distances. Second, inductance. The magnetic field around the conductor causes inductive reactance, which can result in power losses. Proper spacing and bundling of conductors help minimize inductance. Third, capacitance. Capacitance between conductors and the ground can lead to reactive power losses. Optimized tower design and conductor spacing reduce capacitance effects by use of bundled conductors to balance inductive and capacitive reactance. Selection of conductor size and material to optimize transmission efficiency. 2. Corona effects. The purpose is to prevent power loss, reduce noise, and minimize electromagnetic interference (EMI). Some of the explanation are: corona discharge occurs when the electric field around a conductor exceeds the breakdown strength of air, ionizing it, leads to power loss, noise, and radio interference. Design strategies: increase conductor diameter or use bundled conductors to reduce electric field intensity. Maintain adequate spacing between conductors and to the ground. Use high-quality insulators to handle high-voltage conditions. The benefits are to lower power loss, quieter operation, and reduced EMI, ensuring compliance with communication system requirements. 3. Short-circuit capacity. The purpose is to ensure that the transmission line can handle fault currents safely without damage. The key considerations are: fault current handling. During a short circuit, high fault currents flow through the line. Conductors, towers, and grounding systems must withstand these currents without overheating or structural damage. Protective devices, circuit breakers, and relays are designed to isolate faults quickly to prevent cascading failures. Thermal and mechanical stress. The line must be designed to endure the thermal and mechanical stresses induced by fault currents. Coordination with grid. Electrical design must align with grid requirements to maintain stability during faults. By addressing impedance and losses, corona effects, and short-circuit capacity, electrical design ensures that the transmission line operates efficiently, safely, and reliably under all conditions. These factors are integral to maintaining grid stability and meeting energy demand effectively. Reliability and safety. Redundancy. Include parallel lines or other contingencies for uninterrupted supply. Safety standards. Ensure compliance with local and international safety standards, for example, SEIEC. Fault management. Include protective systems like circuit breakers and relays. Regulatory compliance. Local and international standards. Follow guidelines such as NESC, IEC, or regional codes. Environmental permits. Obtain necessary permits for construction and operation. Community engagement. Address concerns of nearby communities regarding safety and aesthetics. These are all the design framework ensures that the transmission line operates efficiently, meets safety standards, and integrates seamlessly into the power grid. As we have understood about detail survey and the contents in Chapter 11, let us understand profile preparation and submission. Once the design team receives approval for the design criteria from the consultant engineer, CE, and detailed survey credentials from the site, they input all the details into PLSCAD. The team then determines the most optimal tower locations, involving several critical steps: I. Tower type selection, 2. Tower spacing, design span, 3. Structural load analysis, IV, SAG calculation, V. Line profile preparation. Let's explore these topics in detail. Tower type selection. Choosing the appropriate tower type, e.g. suspension, tension, angle, or dead-end towers, based on factors such as voltage level, terrain and topography, line alignment and angle, environmental condition, span lengths, and conductor type, crossings and obstacles, safety and ground clearance. Proper tower selection is a key factor in the successful execution of a transmission line project, ensuring reliability, safety, and cost-effectiveness. 1. Suspension towers. 2. Tension towers, dead-end towers. 3. Angle towers. 4. River crossing grasselform. 5. Transposition towers. 6. Special towers. Common type of transmission line towers. Suspension tower are used in straight line sections where there are no significant changes in direction or mechanical loading. It's lighter and simpler design compared to angle towers. Supports conductors under normal tension without applying extra forces. Typically used in sections with longer spans. Suspension towers are used in straight section to handle minimal mechanical load. Heavier suspension towers are used in high wind or icy areas to withstand wind and ice loading. Tension tower, dead-end tower, are used to terminate the line or where mechanical tension needs to be managed. Heavier and stronger than suspension towers. Designed to hold conductors under high tension, typically at the end of a line section. Often used at substations or river crossings. Tension towers, dead-end, are used near substation or termination to handle high tension and termination loads. Angle tower are used where the line changes direction at specific angles, designed to handle the additional mechanical stress caused by directional changes. Angle towers vary based on the deviation angle, such as 0 to 30 degrees, 30 to 60 degrees, and more. Found at corners or bends along the route. Angle towers are used in sharp bends to handle stress from directional changes. Light angle towers are also used in suspension for long-distance transmission line to balance cost and efficiency. River crossing tower are used for crossing rivers, large water bodies, or wide obstacles. Taller than other types of towers to maintain safe clearance over water. May have special designs to handle longer spans. Typically used with longer spans, 1,000 to 500 meters over rivers. River crossing towers are used for river crossings to provide tall structures for safe clearance and large span length. Transposition tower are used to change the relative positions of conductors to balance electrical properties like inductance and capacitance. Contains additional insulators and hardware to facilitate conductor transposition, common in long transmission lines. Transposition towers used for phase change within the circuit. Special crossing towers are designed for road, railway, or urban crossings where higher clearance is needed. May require taller structures with unique design adaptations for clearance. Tower spacing, design span. Tower spacing refers to the distance between consecutive transmission line towers along the route. This distance is a critical design parameter as it affects the cost, structural requirements, and operational efficiency of the transmission line. The spacing is determined based on various technical, environmental, and economic factors. Depends on voltage, terrain condition, conductor type and sag tension, environmental condition, type of tower, regulatory and safety conditions, balancing cost and safety, cross-section adjustments. Proper tower spacing is a key element in transmission line design, balancing safety, cost, and technical performance. Typical tower spacing guideline. For 33 kV, 80 to 150 meters. For 66 kV, 150 to 200 meters. For 132 kV, 250 to 350 meters. For 220 kV, 300 to 450 meters. For 400 kV, 400 to 500 meters. For 765 kV, 500 to 700 meters. Note, actual spacing may vary depending on terrain, conductor spacing, and other factors. To optimize the tower spacing, following points can be considered. 1. Balancing cost and safety. Longer spans reduce the number of towers needed, but may increase conductor sag, requiring taller towers, and shorter spans increase tower density, leading to higher material and installation costs, but offer greater structural stability. 2. Considering the sag tension analysis. Using tools like PLS-CAD, sag and tension are analyzed for different span lengths to determine optimal spacing while maintaining clearance. 3. Cross-section adjustments. Near obstacles or crossings, spacing is adjusted to maintain appropriate safety distances and compliance with regulations. Tower spacing are affected in special conditions. 1. Hilly terrain. Towers may be spaced unevenly due to varying elevations. Extra towers may be needed in steep areas to support the line. 2. Urban or congested areas. Spacing may be reduced to fit the alignment within limited space or avoid structures. 3. High wind or coastal zones. Shorter spacing and robust tower designs are used to counteract increased wind loading. Structural load analysis. Structural load analysis is a critical process in the design and construction of transmission line towers. It involves determining the various forces and stresses acting on the tower and ensuring the structure can safely withstand them over its operational lifespan. This analysis ensures that the tower remains stable under normal conditions and extreme environmental loads, providing safety and reliability. 1. Typical tower spacing guideline. 2 key steps in structural load analysis. 3. Standards and guidelines for load analysis. 4. Importance of structural load analysis. Types of loads in structural analysis. 1. Vertical loads. These are forces acting downward on the tower due to the weight of the structure and its components. Components of vertical loads are A. Self-weight of the tower, the weight of the steel lattice structure itself. B. Conductor and insulator weight, the weight of conductors, shielding wires, and insulators supported by the tower. C. Additional equipment, loads from items such as line markers, spacers, and vibration dampers. 2. Horizontal loads, forces that act sideways on the tower, primarily caused by environmental factors. Components of horizontal loads are A. Wind load, pressure exerted by wind on the tower, conductors, and insulators. This is a significant factor in tower design. B. Conductor tension, horizontal pulling forces due to the tension in conductors and shield wires, especially at angle or tension towers. C. Ice load in cold regions, the weight of ice accumulation on conductors and the tower, which creates both vertical and horizontal loads due to wind acting on the iced surface. 3. Dynamic loads. These are temporary or fluctuating forces acting on the tower due to external influences. Components of dynamic loads are A. Earthquake loads, vibrations and ground accelerations due to seismic activity. B. Vibration loads, oscillations in conductors caused by wind, known as aeolian vibrations or galloping. C. Short-circuit forces, electromagnetic forces generated during a fault condition in the power line. 4. Other special loads, loads arising during specific events or conditions, such as A. Construction loads, forces applied to the tower during installation of conductors or other construction activities. B. Maintenance loads, additional weight and forces when equipment or personnel are working on the tower. Key steps in structural load analysis. 1. Data collection, environmental data, wind speed, ice thickness, seismic zone information, and temperature variations. B. Conductor data, size, tension, and sag characteristics of conductors and shielding wires. C. Tower data, dimensions, materials, and tower type, e.g. suspension, angle, tension. 2. Load calculation. A. Dead load, weight of the tower, conductors, and accessories under normal conditions. B. Wind load, calculated using wind speed, drag coefficients, and exposed surface area of the tower and conductors. Follows standards such as IS 875, India, or ASCE, American Society of Civil Engineers, for wind loads. C. Ice load, determined based on ice thickness and the surface area of conductors and tower members exposed to icing. D. Dynamic load, seismic loads are calculated using earthquake zone data and structural response factors. 3. Load combinations. To account for extreme conditions, different combinations of loads are analyzed, such as A. Normal conditions, dead load plus wind load under normal operating conditions. B. Extreme conditions, dead load plus maximum wind load plus conductor tension. C. Special conditions, ice load plus wind load during icing events. 4. Structural modeling. A computer model of the tower is created using structural analysis software such as PLS Tower, SAP 2000, or STAAD Pro. The tower's geometry, material properties, and load conditions are input into the model. 5. Stress and deflection analysis. The analysis determines A. Axial forces, compression or tension in the members. Bending moments, forces causing tower members to bend. C. Shear forces, forces acting perpendicular to the cross-section of tower members. D. Deflections, movement or displacement of the structure under load. 6. Safety factor evaluation. Safety factors are applied to account for uncertainties in material properties, environmental conditions, and load calculations. Towers are typically designed with a safety factor of 1.5 to 2.0 for ultimate load conditions. 7. Tower optimization. Based on the results of the load analysis, the tower design may be adjusted to A. Reduce material usage and cost. B. Strengthen members experiencing excessive stress. C. Minimize deflection or swaying under wind loads. Standards and guidelines for load analysis. 1. IS 8 India, Guidelines for Transmission Line Tower Design and Load Calculations. 2. ASC Manual of Practice, Standards for Transmission Structure Loadings. 3. IEC 62826, Guidelines for Structural Design of Overhead Lines. 4. NES, National Electrical Safety Code, Load and Clearance Standards for Power Lines. Output of structural load analysis. 1. Structural drawings, detailed plans of the tower showing member dimensions, bracing, and connections. 2. Load distribution reports, charts and graphs showing how forces are distributed across tower members. 3. Stress and deflection data, values of stress, bending, and deflection at critical points in the tower. 4. Safety assessments, confirmation that the tower can withstand expected loads with adequate safety margins. Importance of structural load analysis. 1. Ensures structural stability, prevents failure due to excessive stress or environmental conditions. 2. Optimizes material usage, balances strength requirements with cost efficiency. 3. Enhances safety, protects personnel, equipment, and nearby structures from potential hazards. 4. Prolongs tower life, ensures the tower can withstand decades of operation under varying conditions. Structural load analysis is an indispensable part of the transmission tower design process, providing the data and confidence needed for safe, reliable, and cost-effective construction. SAG calculations. SAG refers to the vertical distance between the lowest point of a conductor and an imaginary straight line between the two supporting towers. Proper SAG calculation is essential for ensuring the transmission line operates safely and efficiently. Too little SAG can cause excessive tension in the conductor, risking mechanical failure, while too much SAG may result in inadequate ground clearance or midspan clearance violations. 1. Why SAG calculation is important. 2. Factors affecting SAG. 3. SAG calculation methods. 4. SAG tension chart. 5. Regulatory standards for SAG and clearance. 6. Practical considerations for SAG management. 7. Importance of proper SAG calculation. Why SAG calculation is important. 1. Ensures adequate ground clearance, maintains safe distances between conductors and the ground, buildings, or vegetation, prevents safety hazards, especially during extreme weather conditions like high winds or ice loading. 2. Prevents mechanical failure, optimizes the tension in the conductor to prevent snapping or damage to towers and insulators. 3. Regulatory compliance, meets clearance standards set by national and international regulations, example, IS 56 and 13 in India, IEC standards. 4. Efficient operation, maintains the line's electrical and mechanical stability, minimizing energy losses and avoiding structural damage. Factors affecting SAG. 1. Span length. The longer the span between towers, the greater the SAG. 2. Conductor weight. Heavier conductors, e.g. aluminum or steel reinforced, cause more sag. 3. Tension. Higher tension reduces sag but increases the risk of mechanical stress on the conductor and towers. 4. Ambient conditions. Temperature. Conductors expand in hot weather, increasing sag. Wind load. High winds can increase tension, reducing sag temporarily. Ice loading. Ice accumulation adds weight, increasing sag. 5. Material properties. Elasticity and modulus of elasticity of the conductor affect sag behavior. Sag calculation methods. There are two primary methods for calculating sag. 1. Parabolic equation method for small spans. This method assumes the conductor forms a parabola, which is accurate for spans less than 300 meters. The sag S can be calculated using the formula where W equals weight of the conductor per unit length, m faramember, L equals span length, m, T equals horizontal tension in the conductor, N. Two catenary method for long spans. For longer spans, the conductor forms a catenary curve and the calculation becomes more complex. The sag S is given by where cos h equals hyperbolic cosine function. Other variables are the same as above. This method accounts for more precise conductor behavior, especially for high voltage lines with long spans. Three. Temperature and sag. Since conductors expand and contract with temperature changes, sag varies accordingly. The sag under a specific temperature is calculated using the following adjustment formula, where St sag at temperature TTT, SNO sag at the reference temperature, Alpha equals coefficient of thermal expansion of the conductor material, L equals span length, delta T, difference in temperature. Steps in sag calculation. 1. Collect required data: conductor type, weight and elasticity, span length and tower spacing, environmental conditions, e.g. temperature, wind, and ice loading, clearance requirements, e.g. ground, road, or river crossings. 2. Determine conductor tension. Calculate the tension needed to maintain structural integrity and meet clearance requirements. 3. Apply sag formula. Use the parabolic or catenary method based on the span length. 4. Adjust for environmental conditions. Account for temperature expansion, ice loading, and wind forces to ensure sag remains within safe limits under all conditions. 5. Verify against standards. Check calculated sag against regulatory clearance requirements and safety standards. Sag tension chart. To simplify field operations, sag tension charts are often created, showing the relationship between sag, tension, temperature, and span length for specific conductors. These charts allow field engineers to quickly determine the appropriate sag during installation. Regulatory standards for sag and clearance. Under normal conditions, 6 to 7 meters, varies by voltage levels. For road crossings, 7.5 to 8 meters. For railway crossings, 12 meters. And for river crossings, 10 to 15 meters. Compliance with these standards ensures public safety and prevents accidental outages. Practical considerations for sag management. 1. Sag adjustment during installation. Conductors are installed with specific tension, accounting for temperature and anticipated environmental loads. Stringing charts and tension meters are used to achieve precise sag values in the field. 2. Monitoring sag over time. Periodic inspections ensure sag remains within limits as conductors age and stretch. 3. Dynamic sag control. Advanced transmission lines use dynamic monitoring systems to adjust tension automatically under varying conditions. Importance of proper sag calculation. 1. Safety. Prevents contact with ground, structures, or vegetation. 2. Efficiency. Reduces power loss by maintaining optimal conductor height. 3. Longevity. Minimizes mechanical wear on conductors and supports. 4. Regulatory compliance. Ensures adherence to safety and clearance standards. Accurate sag calculation is essential for the safe and efficient operation of transmission lines, balancing mechanical and electrical requirements effectively. Profile preparation. The profile provides a visual representation of the transmission line's path, showing towers, conductors, sag, and terrain. It highlights critical points where extra clearance or adjustments in tower height may be required. Alongside the profile, the team develops a tower spotting plan, detailing the positioning of each tower along the route, specifying type, height, and foundation requirements. Optimize spacing between towers to balance structural integrity and cost effectiveness. Weight spans calculated to ensure stability, especially in regions with uneven terrain or crossings. Before finalizing, the first profile and tower spotting are reviewed and verified by the design team, consultant engineers, and the client. This process includes cross-checking alignment, clearances, and terrain profiles, incorporating feedback from stakeholders or adjusting for new constraints, e.g., permissions, unforeseen obstacles. Ensuring compliance with standards such as IS, Indian Standards, IEC, International Electrotechnical Commission, or other local guidelines. Once agreed upon by the CE and the client, the finalized profile is submitted for their approval by the contractor. Profile submission and approval. The submission of a transmission line profile to the consultant engineer, CE, and client marks a significant step in the project lifecycle. This process ensures that the proposed alignment, structural designs, and engineering details are reviewed, verified, and approved before proceeding to construction. Validation. The CE and client validate that the line profile adheres to technical, environmental, and regulatory requirements. Accuracy check. Ensure that the profile reflects accurate terrain data, tower placements, sag curves, and ground clearance measurements. Approval. Obtain formal approval for the finalized transmission line alignment and associated design elements, allowing the project to advance to execution. Physical and digital documentation. A detailed hard copy and digital soft copy of the profile are submitted to the CE for review. The submission includes alignment drawings, elevation profiles, structural design data, survey findings, and justifications for any deviations. CE review process. The CE conducts both physical inspections, field visits, and electronic reviews of the submitted profile. Focus areas include verification of alignment accuracy against survey data, adequacy of clearances and structural design for the terrain and environmental conditions, consistency with project specifications. Joint inspection with the client. Site visits. The CE and client, often accompanied by the contractor or survey team, inspect critical areas along the proposed alignment, such as crossings and angle points. Feedback collection. Observations and suggestions from the client and CE are documented for adjustments if necessary. Full or partial approval. If the profile meets all requirements, the CE and client issue full approval, allowing construction to commence. For unresolved sections, e.g., areas awaiting permits or clearance, partial approval is granted, specifying required modifications. Revisions if needed. The survey or design team revises the profile to address any discrepancies or client CE feedback. Resubmission is done for final approval. Key deliverables in the submission. 1. Profile map. Detailed topographic map with alignment, tower locations, and span lengths. 2. Elevation and clearance details, sag profiles, ground clearances, and conductor specifications. 3. Crossing data, detailed drawings and clearances for roads, rivers, railways, and other infrastructure. 4. Tower spotting plan, tower positions with specifications for height, type, and foundation requirements. Environmental compliance report, documentation of adherence to regulations for vegetation, wildlife, and protected zones. 6. Technical justifications, explanation of design decisions, including any deviations from the initial alignment plan. Importance of profile submission. 1. Technical accuracy. Ensures the transmission line is designed for optimal performance and stability. 2. Risk mitigation identifies and addresses potential issues such as improper clearances or unstable terrain. 3. Compliance verifies adherence to regulatory, safety, and environmental standards. 4. Client satisfaction involves the client in the review process, ensuring alignment with their expectations. Approved profile. With approval, the contractor can proceed to the construction phase with confidence, knowing the design is verified and optimized. Action plan for unresolved issues. Partial approvals outline specific steps to address pending concerns without delaying other project areas. Profile approval. The CE checks the profile against the design criteria, ensuring the proposed tower placements and terrain adjustments are technically sound. If the profile is approved, the contractor can proceed with further activities. If clarifications or changes are required, the profile is returned for revision and resubmitted for approval. Essential terms to understand. Understanding these concepts to ensures proper design reading, work execution, safety and quality of work, supervision of transmission line. Each term plays a critical role in engineering calculations, tower placement, and line stability. Design span, ruling span, wind span, weight span, uplift, shielding angle, wind pressure, hilly terrain, ground profile, null point, ground clearance, cold curve, supporting foot curve, hot curve, initial sag, final sag, creepage of conductor. Design span. The design span is the standard distance between two consecutive towers used as the basis for structural design calculations. It is an idealized length representing the average span length of a transmission line and helps in determining tower heights, sag, and tension. Example, in a line with varying spans, the design span ensures uniformity in calculations for safety and reliability. Ruling span. The ruling span is the equivalent span length that represents the mechanical behavior of the entire line. It is calculated as the weighted average of all span lengths along a section, accounting for conductor tension and sag. It ensures uniform sag-tension relationships across varying spans. Formula, as mentioned, and where L equal individual spans. Wind span. The wind span is the horizontal distance between 2 points where the wind load acts on the conductors. It's calculated by considering the average distance between spans that experience the same wind pressure. Determines wind-induced forces on conductors and their effect on towers. Weight span. The weight span is the horizontal distance between 2 points where the weight of the conductors creates vertical loading on the tower. Critical for designing tower foundations to handle downward forces due to conductor weight, ice loading, and sag. Uplift. Uplift refers to the upward force experienced at tower foundations or insulators caused by excessive tension in conductors, often in hilly terrains or steep profiles. Occurs when conductor weight in the adjacent span exerts upward tension, typically at angle or suspension towers. Shielding angle. The shielding angle is the angle formed between the top of the tower, shield wire, and the conductors below it. Ensures that the ground wire effectively protects conductors from lightning strikes. Smaller angles provide better shielding, but may require taller towers. Wind pressure. The force exerted by the wind on conductors, towers, and insulators. Measured in N-pointers, it is a critical factor in tower and conductor design. Wind load increases with tower height, span length, and conductor surface area. Ground profile. The ground profile is the elevation and terrain layout along the transmission line route, essential for designing tower heights and maintaining proper sag and ground clearance. Null point. The null point is the point along the conductor span where the resultant tension in the conductor is zero. Occurs due to equal tension from both sides of the tower, often near the lowest point in a sag curve. Ground clearance. The minimum vertical distance between the lowest conductor and the ground or any obstruction. Ensures safety and complies with regulatory standards to prevent electrical hazards. Example, minimum clearance over a road is often set to 7.5 meters or more. Minimum clearance refers to the required safe distances between the conductors of a transmission line and the surrounding objects, structures, or ground to ensure safety, reliability, and compliance with regulatory standards. These clearances are crucial to avoid electrical hazards, maintain system integrity, and account for environmental conditions. Cold curve. The cold curve represents the shape of a conductor at its minimum operating temperature, showing minimal sag. Important for initial stringing and calculating tension during cooler conditions. Supporting foot curve. The supporting curve or foot curve shows the idealized shape of a conductor span between two towers without considering sag, used to visualize the alignment and structural behavior of the conductor. Hot curve. The hot curve is the shape of the conductor under maximum operating temperature, showing maximum sag due to thermal expansion. Crucial for verifying ground clearance under high load conditions. Initial sag. The sag in a conductor immediately after installation, before the conductor undergoes long-term effects like creep, based on the initial tension applied during stringing. Final sag. The sag that develops over time after the conductor has experienced creep and operational stress, always greater than the initial sag and is used for long-term performance calculations. Creepage of conductor. Creepage refers to the slow, permanent elongation of the conductor over time due to sustained tension and environmental conditions. Affects sag and tension, requiring compensation in long-term design. Hilly terrain refers to transmission line alignments passing through uneven or sloped landscapes. Requires specialized design considerations, shorter spans for stability, taller towers to maintain ground clearance, extra anchoring to prevent movement due to landslides or soil instability. In this chapter, we covered the essentials of profile plotting, along with key aspects of profile and tower plotting. This concludes today's technical discussion. In the next chapter, we will continue with the remaining topics related to surveying. In our study program, we have consistently emphasized the principles of professional ethics, covering all related topics in previous chapters. We have also introduced the subject of legal compliance and plan to explore additional areas, including human resources, HR, and health, safety, and environment, HSE, in future chapters. Today, as a continuation, we will delve into legal compliance in corporate business for professionals and staff. This new topic aims to provide valuable insights, and we hope it will be beneficial for all our viewers. Legal compliance refers to the adherence to laws, regulations, standards, and ethical practices that govern corporate activities. For corporate professionals, understanding and following these requirements is essential for maintaining the integrity, reputation, and success of both the individual and the organization. Legal compliance is a critical component in corporate governance and business operations, helping professionals navigate complex regulatory environments, avoid legal issues, and ensure ethical business practices. Let us understand the aspects of legal compliance for corporate professionals. These are following topics we will be covering in our chapters. 1. Relevant laws and regulations. 2. Corporate governance and ethical standards. 3. Compliance with employment laws. 4. Data privacy and protection. 5. Anti-corruption and anti-bribery laws. 6. Environmental compliance. Till this point, we have covered in our earlier chapters. Today, our topic is financial and tax compliance. Later in our chapters, we will cover on the following topics: intellectual property (IP) compliance, implementing legal compliance in the workplace. Financial and tax compliance is a critical aspect of legal compliance for transmission line construction projects. Adherence to these requirements ensures that the project operates within the legal framework of the governing authorities, mitigates financial risks, and avoids penalties. Here is a detailed explanation of financial and tax compliance within the context of such projects. Financial compliance. A. Budgetary controls and reporting. The purpose is to monitor project costs and ensure that spending aligns with the approved budget. And the key practices are: maintain transparency in all financial transactions, track expenditures against planned budgets regularly to avoid cost overruns, provide regular financial reports to stakeholders, including clients and regulatory bodies, follow approved financial structures as laid out in project agreements. B. Payments to vendors and contractors. The purpose is to ensure timely and accurate payments while adhering to contractual obligations. The key requirements are: maintain documentation for every transaction, for example, invoices, purchase orders, validate payments with joint measurement certificates or verified work completion reports, ensure compliance with labor laws regarding employee wages and benefits, use approved payment methods to avoid legal issues related to financial fraud. C. Financial audits. The purpose is to verify that financial records are accurate and compliant with local and international standards. And the key practices: conduct regular internal audits during the project lifecycle, ensure external audits are carried out by certified agencies when required, address discrepancies immediately, and document corrective actions. D. Funding and loans compliance. The purpose is to adhere to terms associated with project financing, particularly if external loans or government grants are used. And the key considerations: fulfill repayment obligations on time to avoid penalties, maintain transparency in the utilization of funds as per agreements with financiers, submit periodic financial utilization reports to funding agencies. Tax compliance. A. Tax registrations. The purpose is to ensure the company and project are registered with the relevant tax authorities before operations begin. The requirements are: register for local and national tax identification numbers, comply with GST VAT, goods and services tax, value-added tax regulations, if applicable. For multinational projects, comply with international tax laws, including double taxation treaties. B. Withholding taxes. The purpose is to ensure proper deduction and payment of taxes on employee salaries, vendor payments, and contractor services. And the key practices are: deduct taxes at the source as per applicable laws, submit withholding tax returns to the authorities on time, provide employees and vendors with Form 16 or equivalent tax certificates. C. Indirect taxes. The purpose is comply with taxes such as GST, VAT, or sales tax on goods and services used in the project. The key practices are: maintain detailed records of all tax-related transactions, invoices, receipts, regularly file tax returns and pay taxes within the stipulated deadlines, claim input tax credits wherever applicable. D. Corporate taxes. The purpose is to ensure that the company pays taxes on its profits as per local and international corporate tax laws. The key practices are: submit corporate tax returns annually or as required, maintain accurate financial records to determine taxable income, use tax optimization methods that comply with legal frameworks. E. Customs and excise duties. The purpose is to adhere to customs regulations for imported equipment or materials, and the key considerations are: ensure all imported goods are declared and duties are paid, obtain necessary customs clearances for specialized construction equipment. The key benefits of compliance are avoidance of legal penalties, ensures the project is not subjected to fines or legal actions. Reputation management maintains the company's reputation in the industry by ensuring transparency and accountability. Efficient resource utilization reduces financial waste through proper monitoring and reporting. Stakeholder trust builds confidence among clients, contractors, and funding agencies. Business continuity ensures smooth project execution without interruptions due to non-compliance. The best practices for financial and tax compliance are: use technology, employ accounting and compliance software, eSage 300, SAP, for accuracy. Hire experts, engage tax consultants and auditors for complex financial matters. Training, train employees on financial and tax regulations applicable to the project. Documentation, keep comprehensive records of all financial and tax transactions for audit purposes. Regular updates, stay updated on changes in financial and tax laws to ensure ongoing compliance. By adhering to financial and tax compliance requirements, transmission line construction projects can achieve operational efficiency, legal security, and financial transparency, ensuring their long-term success. Today's quote is from Tony Dorsett. To succeed, you need to find something to hold on to, something to motivate you, something to inspire you. This quote emphasizes the key elements required for success: purpose, motivation, and inspiration. Something to hold on to. This refers to having a strong foundation or anchor in life, be it your values, goals, dreams, or even the support of loved ones. It provides stability and direction, especially during challenging times. Something to motivate you. Motivation is the driving force that pushes you to take action. It can come from internal factors like self-improvement and ambition, or external factors such as achieving recognition or fulfilling responsibilities. Something to inspire you. Inspiration is the spark that fuels creativity and passion. It often comes from role models, experiences, or a vision of what you aspire to achieve. Inspiration keeps you engaged and passionate about your journey. Success is not just about working hard, but also about being connected to what matters most to you. When you have something to believe in, hold on to, a reason to act, motivation, and a source of creativity and passion, inspiration, you are more likely to persevere and achieve your goals. It's a reminder to align your actions with your purpose and find meaning in your efforts. As we wrap up our session, I encourage you to subscribe and hit the bell icon so you won't miss any of our upcoming chapters. It's your gateway to mastering transmission line supervision. That brings us to the end of today's Chapter 12, and we are in the phase of understanding about survey activity. In our next chapter, we will be completing the remaining part. Until then, take care, and thank you for watching.